Then welcome back to our lecture on quantum information theory. And let's first briefly recall what we did last time. So we started introducing quantum operations, and in particular what we considered in the beginning were quantum operations which are maps between density operators and density operators. So a map which maps a density operator to a density operator. And we started with a so-called system environment model, in the sense that we considered a system together with the environment and said that together they undergo a unitary transition. But in the end, we are only interested in what happens to the system, so we have to trace out the environment after this unitary transformation. And what we saw is that we can describe this via a so-called operator sum representation. Okay, it's also called a Kraus representation. And vice versa, we then proved that given such an operator sum representation, you can always find a system environment model which gives rise to this operator sum representation. So this was the first part of the last lecture, and in the second part, we then took a look at more general quantum operations. Namely, we considered quantum operations which have as the domain and range the whole Hilbert space. So now not necessarily the subset of density operators on this Hilbert space. Right? And then we formulated three conditions which are which must be satisfied in order that we say that this is a quantum operation, right? So these three reasonable assumptions were as follows. Let me recap this. So we said that any quantum operation E, which has as domain and range the Hilbert space, must satisfy the following. So the first condition we call P1, and it says that E must be completely positive. Meaning that E of A must be positive for all positive operators A, and A living on the Hilbert space H, and that the identity tensor E acting on B must also be greater than 0. So this first condition is positivity, and the second is completely positivity. So this must be also positive for all positive B's, where B is an operator on a Hilbert space HE, so which we usually associate with the Hilbert space of the environment and our Hilbert space of the principal system. And then secondly, we said as a condition that P2 was that the trace of E satisfies that 0 smaller equal to trace of E, okay, say A small equal 1. And this means that if this is equal to 1, then it describes all possible transitions. If it's smaller to 1, then with our description of these quantum operations, we miss some transitions. So in the end, it states that probabilities can never sum to a number greater than 1, right? And then the third condition, P3, was linearity, namely E must be linear. Which means that E of an ensemble, sum over K, P, K, rho K, must be equal to sum over K, P, K, E of rho K for all probabilities P, K greater equal to 0, and these probabilities summing to 1. Okay, so this is where the conditions, and well, this let me say it again. These are reasonable assumptions for general quantum operations, which domain and range the full Hilbert space, right? So these are actually very little assumptions, so to say. We only assume complete positivity, then that the trace lies between 0 and 1, and linearity. Linearity is clear because quantum mechanics is linear, and the other assumptions are also reasonable. And from this, we then formulated the Kraus representation theorem. So let me briefly recall this. So it was theorem 3.2. And it states that any quantum operation let's formulate it differently. The map E satisfies these three conditions, P1, P2, and P3, if and only if it has an operator sum representation E of rho is equal to sum over J, Ej rho, Ej dagger. This was 3.18 for some operators Ej with these operators being linear and the sum of Ej dagger, Ej being smaller equal to the identity. Okay, so this was the Kraus representation theorem that we stated the last time, and what we're going to do now is we prove this theorem. Okay, that's why I wrote it down, that you see it again, and we're going to prove it now. And as you see, it's an if and only if condition, so we have to prove both directions. Okay? And we start the proof with the backwards direction. So let's assume that that we have E of rho is equal to sum over J, Ej rho, Ej dagger with Ej linear and the sum of these operators Ej dagger, Ej being smaller equal to the identity. Okay, so this is what we assume, and what we want to prove now is that from this assumption it follows that P1, P2, and P3 holds. Okay, so this is the backwards direction. So we start with P1, which we start with P3, which is the linearity. So we consider E of sum over K, Pk rho K. So let's write this down here with the sum over J. Then we have Ej, and here we have sum over K, Pk rho K, and then Ej dagger. And now we know that Ej is linear, okay? This is what we assumed in the beginning. So since Ej is linear, we can write this as sum over K, Pk, and then sum over J, Ej rho, Ej dagger, which is sum over K, Pk E of rho K. I missed the K here. Yeah. Okay, So this proves that P3 follows. Next, what we do is we prove P1. Okay. Okay, for P1, let us first suppose or consider any operator B living on HE tensor H and any state psi which also lives on HE tensor H, and let us define the state phi j as being 1 tensor E j times psi. Okay, so we simply came up with a general operator, and we defined it. We came up with a general state, and then we defined this phi j in this way. And what we now do is we rewrite B in a decomposition form that we considered in equation. Let me look this up. 139. So we write B is equal to sum over K, and then we have some coefficients Bk, and then Be living in the subspace He. We have some coefficients K tensor Bs living in the substate described by our principal system H. So this we did state that any operator living on a composite system can always be written in this form, and this we stated in equation 139. So we write B in this form and consider the following, namely psi, and then okay, and then the map 1 tensor E, so B mapped by this quantum operation, and then cat and bra psi. And now we insert this form of our operator. So we have psi, and then we have 1 tensor E of sum over K coefficients Bk, Bk tensor Bsk. And as a next step, we use that E is linear, because this we already showed in P3, right? So we can use that E is linear. And this gives us then psi, and then we have here sum over K Bk Bek tensor E of Bsk. And as a next step, we use that this can be written in this form with our operators Ej, right? So we have psi sum over K Bk Bek, and then here tensor sum over J Ej, and then those Bsk E J dagger psi. And we rewrite this in the following form, namely as 1 tensor Ej Okay, here I missed a dagger in the definition. One tensor Ej, and then we have sum over j, sum over k, bk, bek tensor sk, and then one tensor Ej dagger psi. Okay, so what we did is we took out this operators Ej together with the identity on the left hand, on the left side, and on the right side we have this Ej dagger and the identity. Okay. And we get this in this form. And next what we do is we identify the state on the left and the right hand side as the state phi j, right? So we get sum over j phi j, and what's here is simply b phi j, okay? And as a next step, we know that b is positive, right? And since b is positive, this must be greater or equal to 0. Greater or equal to 0. Okay. So in the last step, we used that b is positive, hence we find that this b mapped by our quantum operation is also positive, because it holds for any psi, right? So we took any psi out of the Hilbert space and showed that this is greater or equal to 0, meaning that our quantum operation must be positive. Hence we find that one tensor E acting on B is positive. Okay, now you remember there are two conditions, so we simply showed the lower one here in P1, and now the upper one is easy because the upper one follows for some choice of B. So the first line in P1 follows by setting B is equal to some operator C tensor A. Okay, this you can actually see pretty easily if you set B as an operator C tensor A. Well, then if we take a look here, so this is B, and if we set this as some C tensor A, then for the C operator we have only the identity acting on C, and for the A operator we then have some state tensor A tensor the state, and this is always greater or equal to 0, and then meaning that from this from the second line follows the first line. I mean, this is also reasonable in the sense that if you take a look at these two lines, then the upper line is a special case of the lower line, right? And this is because of the reasoning that you can choose B as in this tensor form, and then you get the result of the first line. Okay, what's left to prove is now P2, right? So I'm gonna erase this now, but I hope you keep in mind what these three assumptions are. Okay, I'm erasing the other part. It's better. So what we are left is proving P2. And for P2, we use that we can write a positive operator or the density operator in the sense in the spectral decomposition. So with the spectral decomposition, A is equal to, let's write it as sum over J over K, lambda K times lambda K, lambda K. So this is our spectral decomposition of A. We get specify this with lambda k greater equals 0 and sum over k lambda k equals 1. So this we get that the trace of E A is the trace of sum over J E J, and then we have here sum over K lambda K E J dagger. So what we use now is that again that EJ is linear. So we have trace of sum over K lambda K and then sum over J EJ lambda K EJ dagger. Now let's perform the trace such that we get sum over K lambda K, and then we have lambda K sum over J EJ dagger EJ lambda K. And this, we know that this is smaller equal to the identity, right? Because this was one of our initial assumptions, which stands here. So, meaning that this expression is smaller or equal to the sum over K lambda K, which is 1. So we proved that the trace of our quantum operation is bounded from above by 1, right? So this is this bound here. And the lower bound directly follows from this quantum operation being positive, so from P1. Since it's positive, the trace must be always greater or equal to 0. So the lower bound in P2 follows from E of A being positive. Okay, so this finishes now the proof in the backwards direction. Now we prove the forward direction. The forward direction is a little bit more complicated. So first, let us suppose. So let's write down what we can suppose from the beginning. So suppose that P1, P2, and P3 hold. Then define. Let's introduce the space HE with equal dimension as our principal Hilbert space H, and let the states, let me call them J, E, and JS, let this be ON basis, and let be an ON basis of HE and H respectively. Okay, so simply what we did so far is we defined this additional Hilbert space HE, which we usually associate with this environment Hilbert space. And we suppose that this has equal dimension as our principal Hilbert space, and then we introduced simply an ON basis of both of these Hilbert spaces. Okay? Now let me define a not necessarily normalized, maximally entangled state between these two systems. So define the not necessarily normalized maximally entangled state. Let's call this alpha, being sum over all J environment, J system. Let's give this equation a number. This is 322. Okay. But I think now I can erase this board, right? Because what we're doing now is we're proving the forward direction. So we assume these three assumptions, and we want to see that we get an operator sum representation. So we define this maximally entangled state and an operator. We call this sigma, which is 1 tensor E acting alpha alpha. Okay, so we now can assume linearity and plug in equation 322 such that we get the sum over J K, and then we have here J environment K environment tensor E of J system K system. This is equation 323. So what is this actually? It's a one-sided map, right? So we have our state alpha, and this sigma is simply a one-sided operation acting on the state alpha. So, which is the image of alpha under a one-sided channel. Okay. Further, let us now define a general state of the system. So let psi, I think I call it psi s, be Js. Let this state and this be any state in our principal Hilbert space, and define the corresponding state in our environmental Hilbert space, namely as psi e being sum over j now psi star, so the complex conjugation in our basis states of the environment. Okay, so let me stress here one thing that should be clear. Psi s, we defined psi s as any state of in our principal system, right? We wrote it simply as a linear combination of our basis states. That's how we do it. And given this state, we then defined a corresponding state in our environmental Hilbert space, which was the Hilbert space that we introduced, which has the same dimension as the principal system, right? And we defined it in this way that we have the same elements, but complex conjugated. Right? So this is the difference. So for any state in our Hilbert space, we have a corresponding state in this environmental Hilbert space, right? And they have simply complex conjugated coefficients. So, okay, these formal things we now defined in order that we can prove that we get from our assumptions P1 to P3 that we get this operator sum representation, right? And it's not, okay, at first it's not so intuitive why we have to define all of this, okay? But why we have to define this maximal entangled state and this one-sided channel. In the end, I mean, what turns out is that this is a nice way to do it, right? An easy way to do it. So let's continue. And the reason for all of these definitions follows actually now from a very interesting identity. So first, we note the following identity, namely that if I have psi e sigma psi e. Okay, so now note that psi e lives in the Hilbert space of the environmental Hilbert space. Sigma is an operator living in the composite Hilbert space of H and HE, right? So this whole object here then lives in our principal Hilbert space, right? Let's see how this looks like. And to do so, what we insert is this equation 323, which is this one here. So we then have psi e and sum over j k environment k environment tensor e of j environment k environment, and then psi e. Next, we use this equation 325. So it's how we write down this psi e. So let's plug this in here. So this gives us then, okay, if we well, let's write this differently, then we see it better. Let's do one more step. So we have psi e j e and k e psi e, and then e of j e k e. Okay, and now we calculate this scalar product, and this is easy to see with the above. So it's then psi j and then this one is psi k complex conjugated. Okay, and what we now use is the linearity of E. Okay, this was one of our previous assumptions, which is P3. So this was the linearity. So we have then that this is E of sum over j k psi j psi k star j e k e. Okay, and this by equation 324, which is this one here, the definition of, or how we write down psi s, you see that this is nothing else but the map E acting on psi s. Okay, this is equation now 326. So what we find is a nice identity in the sense that we get our operation, our quantum operation, acting on the state psi s, which can be any state, right? Because we assume psi s is any state in our principal system, and we can write this down in this form as a sigma, which was this maximally entangled state with a where we have a one-sided channel operating on it, and then sandwiched by this psi e, right? So this gives us now a nice form how to connect actually the thing that we want to calculate with our previous definitions. So the next thing that we see is we know that our operation E is positive, right? And from this equation, from this identity here, we see that sigma must also be positive, right? Because we sandwich sigma with any state psi E, and we get something positive. So from this we see that sigma must be positive. So from this, and P2, we find that sigma is positive, and can be written in its spectral decomposition. So let's write this as sigma being a sum over j, sj, sj, with not necessarily normalized states sj. So they live in the Hilbert space of both HE and H. So with this now, let us define the following map. Okay, this comes a bit out of the blue, but you will see that this why we define it like this. So we define the map EJ as mapping H to H, where EJ, which takes as an argument psi system, is equal to psi environment Sj. So we call that Sj lives in the Hilbert space in the composite Hilbert space, right? And if we sandwich it from the left with psi e, then we get something which lives in the system Hilbert space, right? So this is a map from the Hilbert space of the system to the Hilbert space of the system. So this is equation 327 and 328. Let's define the map. And this map is linear. The reason is that Ej acting on, for all complex lambda, we have Ej acting on lambda psi s is equal to psi e lambda Sj is equal to lambda psi e Sj is equal to lambda Ej of psi e. Okay, now note that here lambda, we have lambda, and the reason that that we define psi e with complex conjugated coefficients, that's the reason why we get lambda here and not the complex conjugated lambda, right? And then we see that this holds for all complex lambdas. Okay, so because here we have the ket of psi s, and here we have the bra of psi e, right? But the coefficients of psi e are complex conjugated coefficients of psi s, and that's why lambda we do not have to complex conjugate lambda here, right? The second thing for linearity is a sum of the arguments, which is linearness, and Ej acting on, say, psi s plus phi s is equal to psi e plus phi e Sj is equal to psi e Sj plus phi e Sj is equal to Ej of psi s plus Ej of phi s. So we see that the map that we defined here is linear, right? And since it's linear, we write it we write the following shorthand. Hence, we write that the map Ej, which takes psi s as an argument, as simply Ej psi s. Right? I mean, we use this notation for linear operators, and we just showed that this Ej is linear. So with this we find that now taking the sum over Ej psi s Ej dagger. Okay. Now what we use is the definition of our map here. So we write this as sum over j, and then we have psi e sj psi e. Okay, we simply now plugged in the definition of our operation Ej, which we defined here in this way. Okay, and this we can rewrite as psi e, and now the sum over j sj psi e. Okay, and now what you see here is here in the middle. Let's do it like this. We have the eigendecomposition of sigma, which is here. Okay, so let's plug this in. So we have psi e sigma psi e, which was okay. And in the end, what we use is equation 326. Is it still? Yeah, it's here. This one. That psi e sigma psi e is simply our map acting on the state psi s. So it's our map E acting on psi s. So we're almost there, because what we now found is an expression for our quantum operation for a particular pure state psi s in this operator sum representation, right? So finally, what we have to show is that this also holds not only for a single state, but for an operator, so for a whole ensemble. So we find this identity, and let me state that this holds for all psi s of our Hilbert space H. Hence, for rho, let's write this as sum over k, some probabilities pk, and some states psi k. We have that E of rho is equal to E of sum over k pk psi k. Now we'll use P3 which was our initial assumption of linearity. So we can write this as sum over k, pk, and then e of psi k. Next, we use this equation 331, such that we can write this as sum over k, pk, and then sum over j, ej, psi k, ej dagger. Next, we use that ej is linear. Okay. Such that we have sum over j, ej, and then we have sum over k, pk, psi k, ej dagger, and here we have our density operator, so it's sum over j, ej rho, ej dagger. Okay, the reason why we can use that ej is linear is because we defined this ej and we actually showed that it's linear, right? So we can use it. That's the reason why we can use it here. And what we find is the operator sum representation. This is exactly what we wanted to show, but there's one ingredient which is missing. So if you remember the Kraus representation theorem, namely we still have to show that, so we are left with showing that the sum of these operators, ej dagger, ej, must be smaller equal to the identity. Okay, so this is the last ingredient for our proof. To this end, consider the following. So we have considered that the trace of E of rho is equal to trace, so now we can plug in 332 of sum j, ej rho, ej dagger, which is equal to the trace of sum over j, ej dagger, ej rho. And this must be smaller or equal to 1. So by our assumption P2, we must have that this expression trace sum over j, ej dagger, ej rho must be smaller or equal to 1, because this was one of our initial assumptions, namely for all rho. But the fact that this holds for all rho can only be possible if this expression here is smaller or equal to the identity. Okay? So this can only be if sum over j, ej dagger, ej smaller or equal to the identity. Okay, if it's hard for you to see it, we can do an example. Okay, so let me take this in brackets. For example, if rho is pure, say rho is psi psi, then for all psi, we must have that trace of sum over j, ej dagger, ej psi psi, which is psi sum over j, ej dagger, ej psi must be smaller or equal to 1. And I think from this from this expression, it's nice to see that that this can only be if this expression here is smaller or equal to the identity, right? If considering states which are normalized. Okay, this finishes the proof of the Kraus representation theorem. And at this point, I think it's good to do a break. So we meet in 10 minutes, roughly. Okay, let's continue. So before the break, what we did is we proved the Kraus representation theorem. And now we continue. So the next thing we ask is, given an operator sum representation, or say given a quantum operation, is there a unique operator sum representation which describes this quantum operation? Or are there many different operator sum representations, right? So this we're going to ask now. And the answer turns out to be that there is a whole family of operator sum representations which correspond to one specific quantum operation. So there's a freedom in choosing the operation elements, right? And this freedom, as we will see in a minute, is very much related to the freedom of the density operator representation for quantum ensembles. So if you remember back when we introduced the density operator, then we described ensembles of quantum states with the density operator. And we've seen that different ensembles can give rise to the same density operator. Right? And in this case here now, it is such that different operation elements can give rise to the same quantum operation. And this is the so-called unitary freedom in the operator sum representation. So it's now chapter 3.1.4, which is freedom in the operator sum representation. And we formulate the statement now via a theorem. So it's theorem 3.3. The unitary freedom in the operator sum representation So let me state now the theorem, which is essentially what the name is, namely we can choose the operation elements with the freedom corresponding to a unitary. So let now the set E1 to EM and the set F1 to Fn be operation elements. Corresponding to the quantum operation E and F respectively. Let us further now assume that if M and N are unequal, then we add the smaller list with zero operators such that we can assume that M is equal to N, right? So by adding zero operators, to the shorter list, we may ensure m is equal to n. Then the quantum operation E is equal to the quantum operation F if and only if there exists a unitary or a m by m unitary U such that the operation elements Ej are equal to the sum over k of U, j, k, f, k, which is 3.35. Okay, this is the statement. Let me say it again. So we are given two sets of operation elements. If they are of different size, then we add to the smaller set 0 operators, such that we can assume that they have a similar size. And then what we find is that these two operation elements, they generate the same quantum operation if and only if those operation elements are related via a unitary matrix. Right? And this is what we call the unitary freedom. And the proof is essentially based on the unitary freedom of the density operator from quantum ensembles. Right? So the key of the proof is equation 1.28, which states that for normalized states, say psi j and phi k and probability distributions so this is a whole set of states. Okay, they're not necessarily orthogonal, but they're normalized, and probability distributions Pj and Qk we have that the density operator rho can be written as sum over j, Pj, psi j is equal to sum over k, Qk, phi k, if and only if with square root of Pj times psi j is equal to the sum over k U jk square root of qk and phi k. So this was this equation 336 is essentially equation 128. I just recalled it that you have it in mind. So this is for some unitary U. And we now use this to prove the theorem. Okay? And again, you see it's an if and only if condition, so we have to, again, to prove both directions. And we start with the forward direction. And therefore, okay, what we do is in the forward direction, we suppose that the sum over j ej rho ej dagger is equal to sum over k fk rho fk dagger. Okay, this is meaning that E is equal to F. Okay, we start from this, and we want to prove now that from this follows equation 335. So maybe for all rho. So first, we start by defining the not necessarily normalized states. Let's call them Ej equal to sum over L E tensor Ej Ls, and Fj, which is sum over Le, and then we have let's call it Fk Ls, and these L states are simply ON bases of the Hilbert spaces He and H. So where Le and Ls are on this and this is an n basis of He and H respectively. Okay, so we simply defined now these two states, and the reason for this is as follows. Now note that if you write sum over j Ej, then now we plug in this definition 3.37. So we get a sum over j and then Le, or okay, we get a sum over L prime, then Le, L prime E, and then here we get a sum, so this is a tensor product, sum over j Ej Ls L prime S Ej dagger. And now what we use is this fact here, right? That the quantum operations are equivalent. So we can rewrite this here as sum of L prime Le L prime E, and here we can write this as sum over K Fk and then Ls L prime S Fk dagger, which is by equation 337, nothing else but the sum over k, fk, fk. So what you see is that these two ensembles give rise to the same operator, right? And by this fact, we can now use the unitary freedom, which is here stated in equation 336. So thus, by equation 3.36, there exists a unitary U such that we have Ej is equal to sum over k Uj k fk. Now, let me stress again that the states E and F are not necessarily normalized, right? And that's why these coefficients here, we don't have these coefficients, because we're considering not necessarily normalized states, right? So that's why also here are no coefficients. And this we simply did in order to reduce the notation a bit. But what we find is that those states E and F are simply related by this unitary. And from this we can now continue. And with one more step, we can prove this forward direction. And we're doing a very similar trick as in the proof before, in the proof of the Kraus representation theorem. Namely, we now define an arbitrary state, or we take an arbitrary state. So now, for an arbitrary state, say psi s, to write with coefficients psi L, and our basis states Ls. So we define, so for an arbitrary state, we now define the corresponding states in the Hilbert space He, quite similar as before, right? So we say that this has the corresponding state psi E equal to the sum, and now we take the complex conjugated coefficients, and this lives in the Hilbert space He. And with this, we have now that Ej acting on psi s. Okay. Let's now insert this equation 340. So we have that the sum over L, psi L, Ej acting on Ls. Okay, and now we take equation 337 and 341. Still here. Okay, 337 is still here, and 341 also, which is this one here, such that this is psi e e j. Okay. Okay, I think this is hard to see, so let me briefly show this. So we have psi e times ej is equal, now we insert this equation here, so, and then we have psi e, and here the sum over L e times e j L s. Okay. And now with ej being here, so then we have here sum over L prime, and then we have to take the complex conjugated coefficients, which is then psi L, and then here L e prime with L e and e j L s. This gives us a delta because we have also normal basis states. So it's a sum over L psi L and then e j L s. Okay, and this is what's standing here. Okay, with this you see this equality. And now let's continue with plugging in. So here equation 339, it's this one here. So for this ej, we plug in this definition ej. So we have then sum over k, and now our unitaries u, j, k, and then psi e, fk. Well, and now with the similar calculation as I've shown here in orange, we can use 337 and 340 to show that this expression here is simply fk acting on psi s. Okay, so this step here is essentially this calculation. It's the very same calculation. You simply exchange ej with fk and this operator capital Ej with capital Fk, right? And then it's essentially the very same calculation. And what we get out here is now Ej acting on any state psi s being equal to the sum over this with this unitary element and this operator Fk is acting on the same state. Okay. And this is actually what we wanted to show. Namely, we can now, hence we found that Ej is equal to sum over k u j k fk. The reason is that this equality here holds for any state psi s. Right? So we can conclude that we found this, and this is what we wanted to show. So we are left now with the backwards direction. Fortunately, the backwards direction is easier, but we're gonna. I need the other board. So for the backwards direction, we can suppose that Ej is equal to sum over k u j k f k, right? And what we want to show is that given this, we get the same quantum operation, so that the quantum operations generated by E and F are equal. So we then find that the sum over j, Ej rho, Ej dagger. Now let's plug this in. So we have here a sum over j and then sum over k u j k f k rho and sum over k prime u star j k prime. So we have to take the complex conjugated because it's Ej dagger, right? And then f k prime dagger. So let's rewrite this a bit. Sum over k, k prime. And then we have sum over j and u j k u star j k prime. And then here we have f k rho f k prime dagger. Now let's rewrite this here in the parentheses. So we write this as sum over j u j u k prime j. So we now take u dagger, and from u dagger we take the element k prime j, which is equal to the element u star k j prime. Okay. Because the Hermitian conjugate is the complex conjugated and transposed matrix, right? And then we have here u j k. And what you see here, this is nothing else but u dagger u and the element k prime k of this matrix, which we get if we multiply u dagger with u. Well, and since u is unitary, what's standing here is the identity. So it's from the identity matrix the element k prime k, and this is nothing else but delta k prime k. Okay? And from this we get then the sum over k f k rho f k dagger. Well, and this is exactly what we wanted to show. So what we found is that the backward direction is also true, namely that if those operation elements are related by this unitary, then the corresponding quantum operations give rise to the same quantum operation, so they're equal. Right, so this finished the proof. And finally, let me do an example that you see what this means. Namely, consider the following operation elements. So for the operation elements, say we have E1 equal to 1 over square root of 2, and then a projector on 0 plus a projector on 1, and E2 is equal to 1 over square root of 2 projector on 0 minus projector on 1. So this is our first set of operation elements. And our second set, suppose we have F1 equal to the projector on 0 and F2 is equal to the projector on 1. So for these two sets, which are operation elements on our Hilbert space of a qubit. And they are related as follows. Namely, we see directly that E1 is equal to 1 over square root of 2 F1 plus F2, and E2 is 1 over square root of 2 F1 minus F2. So this is equation 3.44. Well, now what we do is we simply check that those, or we simply check whether those operation elements give rise to an equivalent quantum operation. So for this, we have that E1 rho E1 dagger plus E2 rho E2 dagger, so which is our operation E of rho. Now we can plug this in equation 344. So we see this is 1/2 and then F1 plus F2 rho and F1 dagger plus F2 dagger plus 1/2 F1 minus F2 rho F1 dagger minus F2 dagger. Okay. We can multiply this out, so get 1/2, and then we have F1 rho F1 dagger plus F1 rho F2 dagger plus F2 rho F1 dagger plus F2 rho F2 dagger, and for the second term we get plus F1 rho F1 dagger minus F1 rho F2 dagger minus F2 rho F1 dagger plus F2 rho F2 dagger. And then you see that this cancels with this, and this cancels with this. And we are left with F1 rho F1 dagger plus F2 rho F2 dagger, which is equal to our quantum operation F of rho. This is 345. So, and well, you see now that these two different sets of operation elements give rise to the same quantum operation, right? And the reason is that they are related by a unitary transformation, and this we see here, right? Should I write down? So in equation 3.44, we can identify the unitary U is equal to 1 over square root of 2, 1, 1, 1 minus 1, for which E j is equal to sum over k U j k f k, right? So this example shows exactly this case where there is a unitary U which connects these operation elements, and they, as we just showed here, they give rise to the same quantum operation. So I'd like to finish today with one remark. Namely, we now have this nice tool of this operator sum representation, but we never ask how many such operation elements there are, meaning that can we state an upper bound of how many operation elements we need in order to describe a quantum operation. And it's clear that if there is an upper bound, it must somehow be related to the dimension of the Hilbert space. And this is how it turns out, namely, with this unitary freedom that we just proved, you can show that given a quantum operation on a Hilbert space with dimension d, you need at most d squared operation elements to describe any quantum operation. And this you possibly prove in the exercises. So let me simply write this down as a remark, and you possibly then prove this in the exercises. So with the unitary freedom, of the operator sum representation, one can show that all quantum operations E on a Hilbert space of dimension d can be generated by an operator sum representation containing at most d squared elements, meaning that E of rho is equal to sum over j equals to 1, call this to capital M, and then E j rho E j dagger, where 1 smaller equal M smaller equal d squared. Okay. So this is the end of today's lecture. It's been pretty formal and theoretical because we did 2 longer proofs. And next time we then consider some particular quantum operations, such that you can see how this applies to specific sceneries. Okay? So now we set the formal background of general quantum operations, and we can now use this in order to see how we describe specific quantum operations, such as operations which give rise to noise. Say, for example, you have I think the most trivial example, because we considered quantum computation so far, is suppose you have a quantum computer or a circuit with some qubits, and suppose that there's some noise in the qubits, right? And what we're going to describe next time is what kind of noise there is and how we can describe this noise via this operator sum representations. Okay, that's all for today, and I see you next time.